Look at this rendering process. Today, taking a 3D wireframe and turning it into a photorealistic image is a pure software equation. It relies on infinite frame buffers and pixel interpolation to simulate reality. But before the invention of the transistor, filmmakers faced a hard hardware limit. They had absolutely zero computational power at their disposal. To create an impossible image, they couldn't write code or rely on a computer to calculate the math. They had to physically manipulate the laws of optics and mechanical synchronization in the real world. We are going to forensically deconstruct 4 iconic shots to reveal the temporary, highly specialized optical computers built to defeat physics. In 1927, the film Metropolis needed to put live actors inside a massive futuristic city. The depth of field paradox dictates that a camera lens cannot hold simultaneous focus on a 1:12 scale miniature 3 feet away and a live actor standing 30 feet away. One of them will always be blurry. To bypass this limit, cinematographer Eugen Schüfftan designed a physical focal bypass that became known as the Schüfftan Process. This overhead schematic shows the core hardware setup. By placing a partially silvered mirror at exactly 45 degrees to the camera axis, they split the incoming light path. Notice the light paths reflecting here. The precise 45-degree angle reflects the miniature, pushing its virtual distance back to perfectly match the physical distance of the live-action actors. Both the tiny model and the distant humans arrive at the camera's focal plane together. The integration required intense mechanical labor. Engineers painstakingly scraped the silver amalgam off the back of the mirror at exact mathematical coordinates, creating a physical matte line that allowed the live actors to show through the glass. By combining these scales directly in the lens, this workaround created a zero-latency, full-resolution composite directly at the camera gate, requiring absolutely zero post-production. For the 1933 film The Invisible Man, the engineering requirement was mathematically subtracting a moving human body from a live-action plate. Visual effects pioneer John P. Fulton solved this using a specific application of low-albedo optical subtraction. As shown in this high-contrast visualization, the physical capture process was highly restrictive. The actor wore a tight-fitting black velvet suit and performed against a solid black velvet backdrop. Velvet possesses an exceptionally low albedo, meaning it absorbs almost all incident light rather than reflecting it. Watch the light hit the surface. It dissipates instantly. The film negative doesn't record anything in those areas, creating a total, unexposed void in the exact shape of the actor. By double exposing the background plate into that perfect void later, Fulton achieved the mechanical precursor to modern software-based chroma key algorithms. The abstract Stargate sequence in 2001: A Space Odyssey required complex warp-speed motion blur. The compute deficit here was absolute. There was no digital render engine to calculate how light should streak at light speed. Hardware engineer Douglas Trumbull built an automated analog machine from scratch, sourcing precision synchronization motors, heavy industrial drive gears, directly from scientific supply houses. Take a look at this 3D schematic of the slit-scan rig. Trumbull mechanically locked the camera's spatial movement on a set of physical rails to the precise rotation of the backlit artwork sitting behind the slit. He kept the camera shutter completely open. As the camera slides forward, the slit physically moves across the art, translating physical spatial movement into a 2D optical trail directly onto the film plane. This rig acted exactly like a modern render farm. It physically calculated each frame over several hours of automated, mechanical movement. Even today, pulling a digital key from a green screen often results in spectral overlap that ruins fine details like transparent fabric. Yet in 1964, Mary Poppins achieved a highly specific wavelength of light, the sodium D line, sitting at exactly 580 nanometers. Here is the internal light path of their solution. They stripped down an obsolete Technicolor 3-strip camera and retrofitted the optics with a custom beam splitter prism. As the spectrum separates in the prism, the math aligns perfectly. 589 nanometers falls exactly into a chromatic notch, a physical gap between the sensitivity layers of standard color film. The prism diverted only this exact sodium light onto a dedicated black and white strip, while the full color of the actors passed through completely untouched. by filtering light at the sub-nanometer level, algorithmic methods. These mechanical setups functioned as highly specialized temporary optical computers, engineered to physically solve massive visual equations. Compared to modern digital tools, these early machines had a distinct physical advantage. Because they manipulated actual light rather than processing code, they operated at the physical speed of light, achieving true zero latency. Modern software provides infinite flexibility, but rendering algorithms still spend immense amounts of compute time just trying to emulate the raw optical physics that these analog methods captured by default. When computational power is absolute zero, human ingenuity shifts the entire processing load directly into the physical world.